Okay, so backing up to my mistakes from yesterday, I've actually deleted the pages that have the mistakes and replaced them with doing it correctly. So you can't look back on this, although you can go back to the old YouTube video to see the mistakes. But my mistakes stem from not including that second term correctly in my integrals. So all of this here for the normalization, that was correct this time around. And so here's what it should have been. So I'm just going to go through this quickly to make sure that you have seen the long, tedious, annoying math done properly. So that at the top is the integral, using Dirichlet's theorem to find the C sub n coordinates. And so as we did before, we got down to this second equation. We had exactly that. And then we tried to do each of the integrals, and that's where I made my mistakes. So notice the square root 24 over L squared is just factored out, and I'm only looking at the black integral, the blue integral, and the green integral. So the black integral here, perfect. The black integral here we have, with the limits there. And then putting in the limits, I wrote in all the terms and then put arrows to 0 for the ones that go to 0. Sine of 0 is 0, obviously. And 0 times cosine of 0 is 0 times 1 or 0. So those two terms went to 0. So that left for the black integral two terms, one that had an L over n pi squared, sine of n pi over 2, and one that has an L squared over 2n pi cosine of n pi over 2. And that cosine term wasn't in what I did yesterday somehow. That's the beginning of my mistakes. And I think I did the same mistake more than one time. So that's the black integral. Now I did the blue integral and I kept the minus sign with it. So in the end, I'm just going to add the terms that are in my equals because I kept the minus sign in my integral. Do you understand what I'm saying there?
Just have to go look at it
later. Well, see, this is in blue here. I have minus this stuff.
Yeah.
And so I put here minus that stuff. So this is including the minus sign in the integral.
Okay.
That's why I have this little minus sign in front of my brackets in the middle, because I copied the one from above. I'm not that exact in my writing. And then put a minus in front of it. And then out here, when I actually put in the limits, the signs are reversed because of that minus sign. And so we now have 4 terms, and none of these terms naturally go to 0 except for the first one, the sine of n pi. And I guess I shouldn't have numbered that one because that one wasn't used because it goes to 0. And then finally, the green integral gives us, that's the simple integral of just sine dx. So that gives us just 2 terms. And then I combine the terms. So I have my square root 25 over L squared put back. So the pink here is the pink here that I had initially. And then the stuff inside the brackets is the, the black, blue, and green. And so you can see from the color coding and from the numbers, putting in the terms from each of those, just collecting by sine, by trig functions. So the first one is sine of n pi over 2, the second one cosine of n pi over 2, and the third one cosine of n pi. And then what you see is these add to 0, and these likewise add to 0. And so the 2 cosine terms just disappear. So yeah, I tried to do each one of them separately and find the values for each one separately and then put them together. And that makes your life a lot harder because then nothing disappears. And so you're left then with the square root 24 over L squared times just that first term. And then you see the L squared and L squared are going to cancel. And you have square root 24 is, of course, 24 is 6 times 4. And so 6 times 4, you can bring the square root of 4 out, and it's a 2 root 4, or excuse me, 2 root 6. So square root 24 is 2 root 6. And then we had a 2 right here. So 2 times 2 root 6 gives us 4 root 6 on top, and squared pi squared on bottom. And then the sine. Now the sine is, it's just every quarter of the way through. So if n equals 1, sine of n pi over 2 is 1. N equals 2, it's 0. N equals 3, it's minus 1. N equals 4, back to 0. N equals 5, it's 1, and so on. So we're only going to have odd answers. The even answers are all going to be 0, and then the odd ones are going to alternate in sign. So I just did the first three here, C1, C3, and C5. And you see that it's 98. Okay, so the way to interpret these, this goes back to Chad asked, what does this look like, in real life? So if we had started our system with that TP function that we did, we have it, C1 is 0.992741. If we want to know what the probability of it being in state 1 is going to be, we take C1 mod squared. And so C1 mod squared is going to give us 0.98553. So it's 98.553% in state 1. State 2, of course, it's 0. It's not at all in state 2. It's not in any of the even functions. State 3 is going to be 1.217% in state 3. And state 5, it's going to be 0.158% in state 5.
So the book says that that's like not actually the proper terminology to use, they say, because it's like all in psi, not in psi n. It says that it's more about like the energy level that it's
well, what he is talking about is the way I was speaking of it and what it really means. What it really means is if you take a measurement, you have 98.553% a measurement of the energy. You have 98.553% chance that it will be in energy state 1.
Okay.
If you take a measurement of the energy, you have a 1.217% chance that it will be in state 3.
Okay.
And so on. That's what he's saying, because that's exactly what it means. Everything else after that starts to be interpretation.
So energy states are what you can talk about?
For what we've done so far, yes.
Okay.
I mean, there's other things that go with this energy state, but yes.
Okay.
Because we say N is telling us the energy state.
Yeah.
So that brings us to a philosophical point here. The entire Schrodinger cat problem. Have I clearly defined the Schrodinger cat problem for the class?
Yeah.
Okay. So that cat problem is illustrating this. The cat, just like this, if you were to measure the cat at the time when it's 50%, if you were to measure the cat 100 times, 50 of the times on average, the cat would be perfectly healthy. And 50 times it would have been dead as a doornail. Right? It's a sick cat. So it's not half sick, half well. It's either fully sick or fully well. But when you make the measurements, that's the percentage of the time you're going to find it one, percentage of the time the other. And then the way we say that in physics is that it's in a superposition state. That is, it's in a combination of the live state and the dead state. And so that's when you start to, you probably have heard the term superposition state, maybe not. And a superposition state means you have multiple states that it's at the same time existing in. But when you measure it, you force it to jump to just one. Okay, now another thing that we that we talked about is the these tell us the probability of being in a specific state. Some of the probabilities had better be 1, right? So if we add these all up, it should come to 1. Now, if you add the first one, you look at the first one, you're like, wow, 98.553%, or 0.98553, excuse me. That's pretty close to 1. And it seems pretty improbable that it's not going to go over 1. But if you look at the next one, 0.01217, you're like, well, that didn't go over 1. Then the next one is a much smaller. And of course, if you just did the limit of the sum, you would determine, nope, it doesn't. In fact, it does come exactly to 1. On a spreadsheet, I actually calculated the first 40 terms. And that's where I got these numbers from, just taking the first 3 off the spreadsheet. And I summed the column to make sure, and yes, they came to within the precision of the spreadsheet, which you have to understand the spreadsheet's only good to 15 decimal places. It came to 1. Now we change gears. Now we're going to move to the harmonic oscillator, or the quantum oscillator. But we're going to start by talking about the simple harmonic oscillator. So simple harmonic oscillator has a force function, force equal to minus kx, because it's a spring. And so since force, according to Newton's second law, is ma, and a is the second derivative of x with respect to time, we have a differential equation here. Oops, that's not going to stay. Who cares? We have a differential equation that looks just like the differential equation we have in the Schrodinger equation, really. And so I want to go through, just to practice the same kind of practice we get with the Schrodinger equation. What should the solution of this look like? What is its form going to be? Right. Right. You haven't had differential equations, but that's what we have. This type of differential equation has a solution of the form e to the bx. So that means if we take the second derivative of x with respect to time squared, we already did this, so we don't have to beat the horse. That's equal to b squared x. And so I get minus kx equals mb squared x, or that. So the solution is either x is equal to 0. If x is identically equal to 0, it's not oscillating, so that's the trivial solution that we throw out. Or we have to have mb squared plus k equals 0, which means b is equal to the square root of minus k over m, which we then identify as equal to I omega, where omega is defined as square root of k over m. So note we instantly have just one frequency. There is one thing that I did not write. It's so easy to forget that I forgot it myself. What did I forget? So we had two solutions here, not just one. So now we have x equals some constant e to the plus some constant e to the minus t. To be consistent with my work above, I'm going to change these constants from a and b to c and d. Right? They're just constants. Those constants, once again, are going to be how you set up the system. You could, for instance, set it up so d is 0 or c is 0. It depends on how you start it. Or, using Euler's relation, we can make this as a sine of omega t plus b cosine of omega t. Right? The constants aren't the same, so that's why I changed the previous one, so I wouldn't have a contradiction. So that's what our solution looks like. Another way of writing this would be c sine of omega t plus phi, where c is the square root of a squared plus b squared. That's probably the easiest way to deal with a wave, right? You just have one sinusoidal function instead of two, and then you have a phase angle. So that's the solution that we get for the simple harmonic oscillator. That's not quantum physics, that's reference, so we can see the difference in our quantum physics. And I'm going to go a few steps further in the reference. For the simple harmonic oscillator, as well as the harmonic oscillator, or the quantum oscillator, you have the potential energy is equal to half kx squared. And of course, the kinetic energy is 1/2 mv squared, with the total energy being the maximum that you get from your potential energy. So you would have the total energy 1/2 k c squared, or if you prefer 1/2 k a squared plus b squared. Because you have energy going between kinetic and potential And when kinetic is 0, the potential energy is your total energy. So that's how you can go to that real quickly. So that's our energy. We have our omega square root k over m, the one frequency. That's pretty much the end of it, I think. That's what I have up here, right? I have the energy state right here. I have the omega. This here is a different way of writing that energy state. And so I'm going to substitute for k just to make sure we see how we get this last state, mostly because that's how we're going to write it for the quantum oscillator. So since k, well, I better start with omega and then go to k. Omega is equal to square root of k over m. Then if I square both sides, then k is equal to m omega squared. And so the last form that was shown up above is just replacing k with m omega squared. Like I said, we're going to have that in our quantum oscillator, so that's why I wanted to make sure we see that. Because simple harmonic oscillator is something that's very dominant in life. So when I say simple harmonic oscillator, I realize right now, for the first time in the lecture, I didn't define simple harmonic oscillator to you. What is a simple harmonic oscillator? Chad should know because Chad came down with Carrie to borrow the equipment to demonstrate this. A simple harmonic oscillator is something that is going in a sinusoidal pattern, one of the ways we define it, or it has a restoring force that's proportional to how much you displaced it from equilibrium. That's the true definition. Has a restoring force, that means that it's pulling it back toward equilibrium, and the strength of that force is proportional to how much is displaced. A spring is the perfect example, hence that's the example we always go to, because the spring has force equal minus kx. So I said that this is something very common. You know, name something in nature besides a spring that is a simple harmonic oscillator.
To be a true, like, harmonic oscillator doesn't have to continue forever.
Well, okay, yes. Everything is damped to some regard. That's true. But what are some other examples you see of very slightly damped simple harmonic oscillators?
The suspension in the car.
Okay, suspension in the car is an example. And in the car, it's more than just lightly damped. You want it to damp out so it doesn't just keep going like this down the road. So you have a higher damping factor there. Anything else you can think of? Chad, who came down and borrowed stuff for chemistry. Why would you borrow that for chemistry, Chad?
Those bond energies or bonding.
The bonding of atoms in a molecule is also basically simple harmonic oscillator. It's not truly, I mean, we're going to be working our way there. We're not going to get to bonding as a long stage problem. But you have a force that, to a first approximation, can be treated as linear when you change the distance, which makes it simple harmonic. Any force, if you have a small enough displacement, you can linearize it. Right? When you have large displacements, not so much. So like a simple pendulum. For small amplitudes, a simple pendulum, we treat as a simple harmonic oscillator. Large amplitudes, well, that linearization was wrong. And so in chemistry, you use it because it's approximately simple harmonic oscillator just for the vibrational states of molecules. So it is something that is very useful, very real, very common. So we're moving from something that's reasonable, the particle in the box, but not really right, to something that's really close to right for many cases in nature. So it's kind of cool to be moving into something that's in the realm of reality. Yeah. So if we do the quantum harmonic oscillator, the quantum harmonic oscillator is going to have the same potential function. So the potential energy is 1/2 kx squared, or 1/2 m omega squared x squared. So we're going to use this form here. Once again, the reason I went ahead and changed it over to that. So the Schrodinger equation, remember this right here, that is V, right? Schrodinger equation is minus h bar squared over 2m, second derivative with respect to position psi, plus potential energy psi is equal to E psi. And from that, we can write the Hamiltonian as, and notice we did something that's almost backward. This term right here, we had originally come to that by saying that kinetic energy, T is the symbol we use for this, the kinetic energy operator should be the momentum operator squared over 2m. Well, now we're going backward on that, and we're saying, okay, we're going to replace that first term with momentum operator squared over 2m. And then the second one, notice this had a single m on top. And so if we divide by 2m, I have to put an m on bottom and another m on top. So that's why it has m squared omega squared x hat squared. Or just m omega x hat quantity squared. So we factored out a 2m, and we've written in terms of the position operator and the momentum operator. At this point in my learning, the only question I could ask was, why? Why did you go and do that? It seemed perfectly fine before. Sure, it's a little shorter here, but it seems more complicated to me like this. How does it resonate with you? Does that feel better or worse or parallel?
Seems, I don't know if it's better, it's just different. I don't really see the point.
Yeah. Seeing the point is something that at this point, if you see the point, you've read ahead. Well, we take, as I like to say, a walk on the wild side. Using mathematical trickery, the Hamiltonian can be rewritten as follows. Now, the Hamiltonian is not written on this page. It's about 3 pages later. But this is the beginning part. So we introduce 2 new operators, A with a subscript plus and A with a subscript minus. And at this point, of course, any reasonable, sane person says, why do you do that? Well, let's think about it if, this is only true if, those weren't operators. If it was just X and P. If this was X and P instead of X operator, P operator, then A minus A plus would be 1 over the square root to H bar M omega minus I P hat plus, oops, no, the first one's the plus. I P hat plus M omega. Oh, I said if they're not operators, so I dropped the operator sign. I didn't give myself space. Life is going well. Speaking of well, Chad, remember to remind me to talk to you after class. Mostly because I don't want you to think I'm an idiot. Because I had a teacher who did what I'm going to do when I was in college, and I thought the teacher was an idiot. I often joke about that situation. Now I'm going to put you in that situation. Okay, so here's what we would have if it wasn't an operator. So now when we multiply, of course, these 2 terms combine to give me 1 over 2 H bar M omega. And then when I do the multiplication, IP times minus IP is minus I squared P squared. Minus I squared is plus 1, so that's P squared. And then I'm going to have this times this is plus I P M omega X. This times this is minus M omega X I P. And then the last one's plus M squared omega squared X squared. We would have that, and what would we do? What would you naturally do with this? Yeah, you would naturally say, well, these 2 terms add to 0. And this is where I say, not so fast, my friends, not so fast. Because those are not X and P, they're operators. Operators can operate on other operators, which is where the commutator homework problems come in. So this is our segue into commutators. But let's just continue if X and P were not operators. That's operators, that last word. Then this would be A minus A plus equals 1 over 2 H bar M omega times P squared plus M squared omega squared X squared. And if we compare that to the Hamiltonian, that would be 1 over H bar omega times the Hamiltonian. But that is not right because these are operators. So now we're like, what do we do with the operator? The commutator, at first I thought this was a real nuisance, and then I decided it was kind of fun doing commutators. So I'm glad I matured. A commutator is a calculation we do to tell us what happens if you flip the order of the operators. And you can always evaluate the commutator without having a wave function. You put a dummy wave function in, and then you calculate what the commutator gives you, and then you can just take it back out. And so we're going to do the commutator for position and momentum. Now I have it here on the slide, but let's get rid of that. Let's do it ourselves. Commutator between X and P. So I put the little hats there to indicate they're operators. That's by definition, I'm going to leave some space. That's by definition, I put the space the wrong place. X hat, P hat minus P hat, X hat. And you look at that and you're like, I don't know what to do. I could replace P hat with what it is. So I could put X hat H bar over I D dx minus H bar over I D dx X hat, but I still really don't have the feel for it. So what we do now is we put in that dummy wave function. If you don't want to write psi, write f. I started to write f. Now it becomes clear. And you're going to love me for this one. This here, H bar over I d dx acting on psi, that's by definition P psi, where P now is the eigenvalue for momentum, or is the observable. And so I'm going to have times x out here. So I have xp psi there. Then for the next one, I have to use the product rule in this derivative, right? Because I have derivative of x psi. So if I do the derivative of x psi, I'm going to have derivative, well, what is, I should have gone one step further. What did I do right there? What's different between the second line and the third line in the second term?
The operator x acting on psi.
Right. The x operator acting on psi gave me the x observable times psi. I had to do that first, so now I can take the derivative. And now I take that derivative using the product rule, and I have, I'm just tired of red. Oh, that should have been X operator. I can move the P past the X operator here. P X operator psi is the same as X operator acting on P psi. And there I did the product rule on the other side, or the second term. There I've expanded the parenthesis. And finally, what is that equal to? That's P psi. So now when I look at this, X and P are now the eigenvalues. So XP psi minus, or PX psi minus XP psi, those subtract out to 0. Because these are no longer operators, they're now values. I know it gets confusing because X is X, it's just if you have a hat on it or not.
Well, but like, so it doesn't change anything to move the X and the P around now that they're no longer?
Now that they're values, no.
Okay.
Because they're not operating on anything.
Oh, so that P is no longer H bar over I.
Correct. It was H bar over I when it had the hat on it. So that's why I said that's where it gets confusing because it looks like the same thing. And if you just read the book, you would probably gloss over the hats and say, I don't see what happened. How come you can subtract them now and you couldn't before? You just made a magic term and then you subtract them? Is that the way it works? So what we have now in the end, I can summarize as X hat comma P hat operate on psi is equal to minus H bar over I psi. Therefore, for any psi, the commutator, so we call this the commutator when it's in the brackets, is equal to minus H bar over I or I H bar. So that's how you calculate a commutator.
So you can just try to take the commutator of any two operators.
Now let's make sure that I have, yes, I do have the same thing up here in the top. Notice in the top I had it in just 2 lines. I wanted to show more lines, not to fill the screen, but to make sure you understand the guts of what was going on behind the scenes in those 2 lines. Right? Once you know what you're doing, you can look at those 2 lines, you're all, yep, there it is, did everything. But before you know, you don't really appreciate what's been done. So let's go ahead and do another commutator just to have some fun. Whoops, don't need, well, yeah, I'll put in 2 pages just to be safe. You can always take them out later. So let's try this. Commutator of xp squared. So I know we're not going to get very far in today's lecture, but it's a long weekend anyway. Look at that and start working on it. See what you get. I want to see you lay it out. So I'm going to sit here and look over your shoulders as you're working on this to make sure that you understand the process.
So, why is there a difference? It's p squared. Would this be squared as well? Or just
Yes, yes.
and then we say that this is p squared.
Yeah, you can do that. You can replace v over I squared with minus 1. So just change that sign to a plus.
Would that be
That's still h bar squared. Yeah, h bar squared. That's the correct answer. But something magical happened here, from here to here.
Well, this is, well, it doesn't need to be product rule.
Yeah, it needs to be product rule. And do one derivative, then do the next derivative.
stuck?
Okay. So this here, that's perfect. And this here shouldn't come back to a negative, should stay positive. But you have separated into two derivatives. X operating on side gives you X times psi. So I drop the operator there. So then we do this derivative. There we go. So that stays the same. And we do this derivative with the product rule. You're going to have psi plus x d psi dx. And then you do this derivative. And so this here and this here is then going to give us p squared x psi. Okay, so I should put p squared x, do that. X operating on side gives me x times psi plus 2h bar squared d dx psi. This one plus this one. Plus x. Well, it's going to be minus x p squared psi. Because I got to put the my sign back in if I go with p. Because the and so these subtract out. I said it was 0, but I'm not getting 0.
Yeah.
So these two subtract out. You see that, right?
Yeah.
You
subtract out, I said it was 0.
She's been listening for a
Yeah,
while.
that's kind of creepy.
It's annoying because I have her muted, right?
Yeah.
When she thinks she's going to help. So we didn't get 0. I was pretty sure it was 0 because x commutes with the Hamiltonian, and that's part of the Hamiltonian. We broke it again. My math is that not what you got? Or did you end up getting 0?
Well, you broke it up in here. That's where okay.
So that was using product rule.
Okay, so you have to use the product rule. Or, like, you can only
Yeah, do one
get
there
on
at a
one.
time.
Okay.
So you're looking for a mistake.
That would be well, I believe we must have it right. It's pretty straightforward math, right?
Yeah.
I was sure that it was 0, but I could be wrong. That's what happens when you pull it out of off the top of your head to do. So let me quickly do my own work here now to just see if we all got the same place. I mean, I know I've looked at yours. So I have x operator. I'm going to throw the psi there. X operator, p operator squared psi minus p operator squared x operator psi. That's equal to x operator p squared psi minus p operator squared x psi. So I did the p squared psi is equal to p squared operator psi is equal to p squared psi, and x operator psi is equal to x times psi. And then this first term is easy because that's p squared x operator psi. Second one, not so easy. And then everything else, so I'll change color for everything else I'm going to do is just in the second term. The first term is done. I know I told you could drop the I squared and replace it with -1, but I'm leaving it here now. Oh, yeah, I think I made a mistake when I worked with you. No, I didn't. Okay, so this term here, I still left as it was, whereas here I let the I squared be -1 and change it to a plus sign. Because those were two of them, I made it 2 h bar squared. And now this final term, p squared x psi minus x p squared psi plus 2h bar squared d psi dx. Because these are now in observables, this here is just 0. And so I have, for our final answer, that. And that's what we found, right? Okay, so that's how a commutator works. Have a great long weekend.